How's it going, guys? This is Ashton Kupka, and this is Introduction to Abstract Mathematics Final Checkpoint. And today we're going to be investigating two theorems, and then first we're going to rewrite them in University Quantified Implication / biconditional format. I'm going to give you some definitions in order to explain things to you guys to help understand what's going on, and then finally I'm going to say what kind of proof is used in the textbook. So the first we're going to look at is going to be result 10.6, which is rewritten in University Quantified Implication / biconditional format. It says, for every relationship between x belonging to the set of all real numbers except the element 2, and y belonging to all the set of real numbers except the element 3, if the function is defined as f of x equals 3x over to x minus 2, then the function is bijective. So the first thing we need to look at is some definitions that you might be unfamiliar with. So the first one is bijective, and then bijective basically just means that the function is both onto and one-to-one. And you're saying, what is a function though? So a function basically is a relationship from one set to another with the property that every element in A is the first coordinate of exactly one pair in F. And then what is injective / one-to-one? And that's basically just saying if there are two distinct elements of the same of a set have distinct images in a different set. So like for every element in the set A, it's going to have a distinct image in a different set. And then surjective / onto, if every element in of the codomain B is the image of some element of A. So basically like every element of B has some corresponding A. And then what kind of proof is used in the textbook? So basically the textbook starts with assuming that that p of x, or the original function, is one-to-one to start off of. So then since it's assuming that the first initial p of x is true, then therefore is using a direct proof. Next, we're going to be looking at theorem 11.4, which rewritten in the University Qualified Implication / biconditional format is basically saying for every infinite set A and B is denumerable, if B is a subset of A, then B is denumerable. And then some definitions that we need to go on is what is an infinite set? So an infinite set is a set that has a never-ending elements. And then a subset actually is going to be a set which is part of a larger set such that all elements of the smaller set belong to said larger set. And then finally, denumerable means if a set has the same cardinality as the set of natural numbers, both infinite and countable. And then what kind of proof is used in the textbook? So if we look at this example here and the proof that it starts with, since it assumes that A is denumerable and B is an infinite set, therefore it's assuming that the initial statement is true and therefore another direct proof. So thank you, I hope you guys learned something, and I'll see you in the next video.